In the previous lecture, we looked at Markov shifts, which was a topological dynamical system. And in this lecture, we want to look at the analog in the realm of measure theoretic dynamical systems. And that analog is Markov chains. Recall that a Markov shift was just the set of all infinite paths through a finite state system. And a finite state system, we interpret it just as a finite directed graph, where the edges, the directed edges, gave us the transition possibilities. Now, a Markov chain is a similar concept, only now that instead of just edges indicating whether we can go from one state to another, we actually have transition probabilities. So we have probabilities that tell us with which probability or what probability we can go from one state to another. So we still have a directed graph, but now instead of fixed edges, so 0, 1 transitions, either there's one or there's none, we have transition probabilities. It's probably easiest to visualize this again with a graph. So assume we have two states, 1 and 2, and now we have transition probabilities. So if I'm in state 1 with probability, let's say P, I go to state 2, and with probability 1 minus P, I stay in state 1. Likewise, if I'm in state 2 with probability Q, I go from state 2 to state 1, and with probability 1 minus Q, I stay in state 2. So for every possible edge that could be present in this two-state graph, so two-vertex graph, right, I have an according probability, right? And the probability distribution is dependent on where I currently am in the system, right? So if I'm in system 1, I have different transition probabilities than when I'm in state 2, where I have transition probabilities Q and 1 minus Q. We can again describe such a system mathematically using matrices. The only difference is now that instead of adjacency matrices, we look at probabilistic matrices. They are also called stochastic matrices, and the condition for a matrix, a K by K matrix being a stochastic matrix, is that all entries are between 0 and 1, but now they can be different from 0 and 1, so they're real numbers. And for each I, we have that the sum of all entries in the ith row, right, is 1. So they give us a probability distribution over the transitions that I can do from being in state I. And the entry Mij then represents the probability that we pass from state I to state J. So in our previous example, we had this two-state system, P, 1 minus P, Q, and 1 minus Q. And the corresponding matrix now would be, so for 1 we have 1 minus P here, and P, which is the probability that I go from 1 to 2, and then Q here, probability that I go from 2 to 1, and 1 minus Q over here. And we see that the sum over all rows, right? So if I take a row and I sum the entries over this row, we get 1. Recall that in the case of Markov shifts, the powers of a adjacency matrix or transition matrix had an interesting interpretation, namely the entries counted the number of paths that could take us from I to j in n steps. Now, this still has a nice interpretation, namely a probabilistic interpretation, namely the ij entry of m to the n is the probability that we can go from state, or that we go from state I to state j in n steps, right? So instead of counting the total number of paths, we are now counting probabilities, so to say. Given such a stochastic matrix M, we can define a process Xn that is based on this matrix M as follows. We start with some initial distribution on the variable x0. So that's just any distribution, probability distribution over the alphabet A. And as usual, now we assume that A is just the set 0 up to k minus 1. So this is the initial distribution. And then we have the joint distributions. So the joint distributions for n greater than or equal to 1, we can specify by giving these conditional distributions, giving the conditional distribution of xn plus 1, right, having value j, conditioned on x0 being I0 up to xn being in. Right. So now the condition, or the definition of this process based on our matrix n just says that this joint distribution here is actually just the conditional distribution of xn plus 1 being j, conditioned on xn being in. And this probability is actually given by the entry min in j, so in the matrix, namely that being in state in, I go to state j as the next state with probability min, j. So you can think of such a process as having a one-step memory, namely that it can only take into account the value of the process which was immediately before the value xn plus 1, right? Namely xn. All the other things do not influence the probability transitions here. And this process xn that we define this way, so initial distribution plus the joint distributions specified in this way, is called the Markov chain given by matrix M. And again, the easiest way to think about such a process is through the visualization via a graph. So let's assume we have here 0 and 1, and we have transition p and 1 minus p, and q and 1 minus q as transition probabilities, right? So now what we have to start with is actually the initial distribution, right? So you can think of this as starting out here at time 0, right? So this would be x0, and suppose we go with probability r, we go into state 0, and with probability 1 minus r, we go into state 1. So that would be the probability, initial probability distribution. So on x0, that would be r and 1 minus r. And then I just think of, you can think of such a process now of the Markov chain as going according to the initial probability distribution either to 0 or 1, and then according to probability distribution p1 minus p, either stay in 0, go to 1, stay in 1, go to 0 according to the q1 minus q distribution, and so on, right? So then I just do a random walk on this graph here according to the distribution. The concept of a Markov chain is, however, more general. So what we have just seen is probably only the most simple example of a Markov chain. In general, a Markov chain is any process that satisfies this one-step memory condition, namely that the joint distribution, the conditional version of the joint distribution, so of the value of xn plus 1 is conditioned on the values of x0 up to xn, right? That this probability is just the same as the probability of xn plus 1 being j, conditioned on the value of xn, right? So only one step memory in the process. So any process of this form is called a Markov chain. And in this definition here, there's nothing specific or special about having a finite alphabet. So we can as well consider general processes, namely revalued processes, that satisfy this condition. So this way, this is then the most general definition of a Markov chain. One can also, as with Markov shifts, one can also look at k-step Markov chains. So by replacing this one step memory here by a k-step memory for any k greater than or equal to 1, right? So now this condition is then replaced by this condition where the value of the probability of the value of xn plus 1 is j, conditioned on the values of the previous variables, is the same as the probability that xn plus 1 takes this value j, conditioned only on the k previous variables. Because of the connections with measure theoretic dynamical systems, we were particularly interested in stationary processes. So when is a Markov chain a stationary process? Well, first of all, the transition probabilities have to be stationary. That means they must all be determined by the same transition matrix. In the most general definition of a Markov chain, these can actually depend on the time n that we're in. So, but the way we define it based on the matrix, we always use the same transition matrix. So these transition probabilities are all stationary then already. So we don't have to worry about later times because there we have stationarity built in by using the same matrix. But what we have to take care of now is that the initial distribution also has to be stationary. Well, this means that the probability distribution of x0 is the same as the probability distribution of x1. So when is that the case? So let's do the following. Let's write the probability distribution of x1. So the probability distribution of x1 being j. That's the same as the probability, so the sum of the probabilities of x1 being j conditioned on x0 being I, and now times x0, the probability of x0 being I, right? And now we sum this from I equals 0 to k minus 1. But now this probability here, this conditional probability, this is exactly the transition probabilities given by our matrix. So here, then this probability distribution is just the sum of the matrix entries times the probability distribution for each I. So now we want this distribution to be equal this distribution here. So hence we want this. We want the probability of x0 being j is the same as this sum here on the right hand side from over all entries in the alphabet, right? So now if we write the initial distribution, right, of x0, so all the probabilities of the values that x0 can take as a row vector, so let's call it p, from p0 up to pk minus 1, then this condition here can be written as just this simple equation here. Pm is equal to a p. right? Because what are we doing here? So here we're taking the inner product of our vector p, right? So notice that I from 0 to k minus 1 with the jth column of m. So here we have the jth column of m. And this has to be equal to the jth entry of our vector p. So it's exactly this condition here. And we call such an initial distribution also stationary. So in the following, when we use the term stationary Markov chain to denote a Markov chain, so we mean that this Markov chain has stationary transitional probabilities, so given by a single stochastic matrix M, and a stationary initial distribution. I would like to finish this lecture with an example, and this example is the Bernoulli-Laplace model for diffusion. So in this model we have two boxes or two chambers, and each of those chambers contains R balls. So here we have R balls, and here we have R balls too. And each of the balls can be either green or red. And in total we have R green balls, and we have also R red balls. Imagine now there's a little opening here between the two chambers, so that there can be some exchange between the chambers. That means we can exchange red for green balls and vice versa. The transition mechanism now is the following. We pick uniformly at random one point here, one ball here, and uniformly at random one ball here, and then we switch them. So here they are switched. We can model this whole affair as a Markov chain as follows. So we say the state space, which is the same as the alphabet, is just the number of red balls in the left side container. So that would be just any number between 0 and R, right? And now what are the transition probabilities? Well, assume I'm in state I and I want to get to state I minus 1. So that means I have I many red balls over here, and I want to decrease the number of red balls by 1. Well, that means I have to, in the transition mechanism, I have to select a red ball over here and a green ball over here, right? And then switch them, right? So the probability of hitting a red ball over here, since we choose everything uniformly at random, is I over R. But the number of green balls over here is just the same as the number of red balls over here. So here, hitting a green ball is also I over R. So the probability is I over R times I over R. That is I over R squared. Likewise, the probability of increasing the number of red balls is similarly computed R minus I over R squared. And the probability of staying with the same number of red balls is likewise, I have to hit a red ball here and a red ball here, right? So here it's I over R, over here it's R minus I over R. So I have the total probability of staying in the same state as I times R minus I over R squared. And since I can at most decrease or increase the number of red balls by at most 1, the probability is Mij 0 for all other pairs ij. So that's a simple but yet important example of a Markov chain, Well, notice here the probabilities really depend on the current state, right? But they only depend on the current state. So it doesn't depend on what the system looked like two switches before, two transitions before that, right? It only depends on the current state.